In section 8.2, we're going to learn how to solve systems of linear equations by using matrices.
A matrix is an array of numbers organized with rows and columns. Notation that we have for a matrix is we surround it with these square brackets. And then this matrix has a lot of numbers in it, and we've given it some subscripts to kind of indicate what's what. So A11, that means first row, first column. If I go to this one, A12, still first row, so across the top, second column. For our purposes, we're going to have numbers in here, these instead of these general placeholders. But this just gives you an idea of what a matrix looks like. We're going to be using what's called an augmented matrix to represent a system of equations. This system has 3 equations with 3 variables. Now notice the equations are all organized where the variables are in the same order if they're present. So this is x, y, z with a number on the other side. X, there are no y's, so they're not listed. Z's with a number on the other side. This one has no x's, but then y and z are still in order with the number on the other side. The augmented matrix takes only numbers out of these systems of equations. Now it's important again that they're in this form, that the equal sign has just the number or constant term on the right, the variables in the same order on the left, potentially with some variables missing if they don't have them in that equation. So let me show you what the corresponding augmented matrix looks like, and then we will discuss where these numbers come from. So with this first equation, there are 4 x's, so there's the 4. It's a subtraction of 6y, so we have to use the sign -6, 1z, and the other side of the equation is 8. So in the matrix, rather than having equal signs, we put this dividing line in between what separates our coefficients for the variables and our numbers. Okay, so then with the second equation, now there's a gap here, but you have to keep the columns set up to represent the same variable. This first column should represent my x's all the way through because this was 4 x's. So in this equation there are 3 x's. My second column represents my y's. The second equation has no y's, so I have to put the placeholder of 0. And then there are -2 z's. The other side of the equation is 0. For the last equation, there are no x's, so 0, 2 y's, 3 z's, and the other side of the equation is 4. So this is the augmented matrix corresponding to this system of equations. The calculator can take a matrix and put it into what's called reduced row echelon form. Now what this form has is it has 1's down the diagonal and 0's on the left-hand side of our augmented matrix everywhere else. Okay, so if we take that resulting matrix from the row reduced echelon form and give equations corresponding to that, that will then tell us the solution to the original system of equations. Here's an example of what row reduced echelon form looks like for an augmented matrix. This one is just one with 2 equations, 2 unknowns, but there are 1's down the diagonal and 0's in the other places to the left of our dividing line here. If I take this augmented matrix and put it back into equations, now I'm not told what variables to use, but we can just assume x and y. So this first column would represent the first variable, let's say x. The second column represents the second variable y. So in the first line I will have 1x, or just x, plus 0y, which would mean just plain old x, equaling 4. And then the second equation I would have 0x, which is just 0, plus 1y, which would just be then y overall on the left, equals -2. And I get the solution x equals 4, y equal -2, because my matrix was in this row reduced echelon form. So The example problems for this section are going to show how to put the augmented matrix into your calculator, how to have the calculator then give it to you in row reduced echelon form, and then now that means you can put down the solution to the system of equations.